in a Rodinger equation, but it's a classical machine learning. It's an overview. I'm going to introduce the original quantum clustering that was developed in 2001. Then I'm going to talk about some improvement based on local length scales. Then we introduce a probabilistic framework that allows to apply a score function based on performance assessment to detect which is the best length scale. And then just the conclusion, drawbacks, and future work. So let's start with the introduction. Okay. Quantum clustering was proposed by David Horn in 2001. The idea is starting from the Hamiltonian, the Rodinger equation, time-independent equation, and it's like an inspiration because it's not exactly the Rodinger equation. It's somehow where the sigma, for instance, here we can see that it's not the physical constant, and it's a length scale parameter associated with the wave function. The idea is just to start with given the wave function, we try to find the potential. It's just the opposite direction in the typical quantum physics, where we define the potential and the energy, and then we try to find with the wave function. Here we do the opposite situation. We assume that the wave function is a percent density estimator that basically is its observation is represented by a Gaussian function with a single length scale. That length scale is the same like here. And the idea is once we got the wave function and some constant energy value, we can develop the potential. And with the potential, the key idea of the algorithm is we can associate the clusters with the potential wells in such a way that the potential in somehow is associated or represents the wave function, and with the potential we can find which are the clusters because we can allocate the observations applying the stochastic gradient descent. We are using adaptive momentum. But the idea is just to allocate all the observations to look for which potential wells go each observation into the potential. So the potential looks something like that. That is the wave function, that is a density estimator. And we can see how the potentials well are associated with the peak densities of the wave function. Why we use the potential instead of the wave function? We could look for a maximum in the high densities, or we can look for potential wells in the potential. The advantage of the potential is because with the gradient descent, if we are far away from the points, the gradient here in the wave functions is practically zero. So it's very hard to find or the convergence of the for the gradient descent with the wave function. But here, with the potential, diverges very quickly, so it's very easy to apply a gradient descent, just playing with the potential. For the purpose of the cluster allocation, with the gradient descent, the offsets values of the potential are irrelevant. We are just looking for the direction of the gradient of the potential. Here, more or less, is a synthetic data, when we can see how is the wave function is the sum of all the Gaussians and looks something like that, where the highest peak is represented with the highest density. And here we can see how it looks like the potential, where it's a bit fuzzy, but we can see the arrows is pointing the direction of the gradient. And we can see here is like a big volcano where it's a big potential well that represents the high density of the points. Here there is other potential well, and here other potential well. The idea of the original quantum clustering is just to associate the potential wells with clusters. And that works very well with non-spherical data, but has some difficulties with the length scale, because sometimes the length scale cannot fit the heteroscedastic data when the local changes in density makes it very difficult to find a trade-off in the length scale. Other difficulties in the original quantum clustering is to find which is the optimal length scale. There is no any tool to select which is the best length scale. So we introduce our improvement that is based on local length scales. That we make two kind of approaches. One based on nearest neighborhoods, like spherical Gaussians, and then a covariance matrix-based Gaussians. So the first approach is just define a length scale that is the mean distance of the k nearest neighborhoods. And that k just represents a percentage of your input data. Here now the wave function is a bit different because we add some normalization term that makes different because each length scale is different from each observation. The potentials is a bit different, it's a bit more complicated. Here we're using like somehow an expected value based on the wave function, and that is the gradient. If we compare the original quantum clustering with the local length scale, we can see that's the original quantum clustering, and we can see how the potential wells here, some points that really didn't belong to that high density cluster are attracted because the single length scale is very difficult to find out a compromise between high density and sparse regions. Here we can see, if we check the cluster allocation, we can see how that high density region are influencing the other neighborhood that really has different densities, but the cluster allocations collects the same cluster. Here we can see that works very well with non-spherical data, but sometimes fails when it has to deal with different sparse data. However, in the local length scale, it's completely different because the wave functions evolves with the density in the input space, and because the wave function is changing, it's evolving, at the same time the potential is also evolving. So here it creates somehow it's like a volcano effect when it creates some kind of walls around the high density region. The effect here in one dimension should be something similar to like that, where there is a sparse region with a potential well, but here there is a high density region here that creates or isolates that region from the rest. So when we apply the cluster allocation, we can see here how that region are isolated from the sparse region here. So when we try to identify which cluster are in which potential well, we can find here one outlier, could be an outlier here, other potential well here, 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 and here. And practically matches that is a synthetic data. We know the true answer, and practically the Jaccard score, that is a supervised index, is 86%, so it's a very good solution. So the next step should be, instead of considering spherical Gaussians, we can approach with a local covariance matrix, just recovering the information of the local manifold information based on that work from Vincent in 2003. And the idea is more or less the same, but instead of spherical Gaussians, we can play with covariance matrices. The problems here is, okay, the wave function is more accurate, that represents the density estimator is very accurate, but adds some complexity in the potential. Because we have to deal with traces, and the calculus, it's a bit complex, but it can be dealt with any program. It's not a problem, but we have to be careful with the covariance matrices to avoid the degeneracy. So we are using the eigenvector basis of each observation just to avoid and apply some regularization term in the diagonal elements, just to avoid divided by 0, and also for making simpler the matrix operations. There is also another problem related with the covariance version of the quantum clustering, is that because the wave functions are anisotropic, when you superpose all the wave functions, it's not like a round or smooth potential and appears some like of local minima, like here, because the superposition is less powerful than with the spherical Gaussians. But we are keeping the same cluster discriminator. Okay, it's working? Yeah. So, yeah. So the solution is more or less similar, but appears on like some local clusters here that they shouldn't apply, but appears. So we need some kind of improvement in the cluster allocation. That is the next step. That is the probabilistic quantum clustering. That is a probabilistic framework that allows to use a probabilistic quantum allocation that works very well. So the idea is to define somehow a joint probability that if we consider that the wave function could be considered like a probability function to find that particle in our input space, and because we already did the cluster allocation in the previous step with the gradient descent, we got all the summation of all the Gaussians are grouped by potential wells. So we can assume that the joint probability of each potential well, or each cluster, and each observation could be considered like that. It's like a subgroup of all the observations that belongs to the same potential well. Once we have defined the joint probability, we can apply all the Bayesian statistics. For instance, if we marginalize over all the real space, we can obtain the probability to find the cluster K in our input space. Also, we can apply the conditional probabilities. For instance, the probability of observe the cluster K given X, or the probability of X given K. We can use the probability of K given X just to apply the probabilistic cluster allocation. It's just we are assigning, for each observation, we're assigning the cluster that gives the maximum probability, the maximum conditional probability. Once we got that, we can allocate new observations. Instead of applying again the gradient descents that we did at the beginning, we can just, because we got a probabilistic model, the new observations in our input space are just assigned to the maximum probability in the new observations. So we speed up a lot because we avoid the stochastic gradient descent. Other thing is with the probability of X given K, we can use like an outlier detection, because we can consider that if we found out that the maximum probability to assign that observation to any cluster is less than a threshold, we could consider that that region belongs to an outlier. Should be something like that. Here is the probabilistic allocation when we erase that situation, what we got here, because we are assigning the cluster that has highest probability. So if that cluster is very few, or is very, the probability to belong to that cluster is lower than that one, we can solve the problems that we got at the beginning with the subclusters that appear here. That is the probability of K given X, and we can see if we observe a zenithal view, which is the boundaries to belong to each cluster, and we can assign any new point. For instance, new point from here, we already know that belongs to that cluster. That boundary defines the highest density region that is defined here, and any new points that are allocated in that boundaries automatically are assigned to that cluster. That is the intermediate cluster, and that is the top cluster. But also we can introduce the outlier detection, just analyzing which is the max probability of assigning each observation to each cluster. So here we can see, it's very dark, but we can see here there is the line with the highest probability to assign to each cluster is less than 5%. So if we consider, for instance, 1% or 5%, all of that regions, there is not enough information to allocate to any cluster. So we can consider that regions are outliers, or in our model we don't have enough information to discriminate or to allocate to any cluster. So we have our probabilistic framework, and now we need to introduce some kind of function that help us to decide which is the best length scale. In the first section, we solved the problem of the length scales with heteroscedastic data, but now it's pending the problem of selecting which is the length scale or the optimal length scale. That can be assigned because it's a probabilistic framework. We can play with the log likelihood function. So if we use the probability, the conditional probability of the winner cluster given the observation, and we apply the log likelihood function, also we can normalize just dividing by n and apply a negative value. So it should be the average negative log likelihood in such a way that we can compare with different data sets because are normalized from between 0 and 1. The good news from that score is that it's empirically correlated with the Jaggers score. So that score is unsupervised, and that score is supervised. So without knowing anything about the true labels, we can find that here the intuition of that score is the lower average negative log likelihood, the better model in terms of probability assigned to each observation. So here we can see how that local minima matches perfectly with the highest, with the best solution if we knew the true labels. So it's a tool it's an unsupervised tool to define which is the best length scale that fits our data. So that is the number of the clusters, that's for additional information, that is the scores, and that is the percentile of neighborhood that we are considering. That model can be used or with the covariance quantum clustering or with the KNN quantum clustering. Both are probabilistic frameworks. But there is other problems where the length scale is not, just tuning the length scale is not enough to obtain the optimal solution. Here is the typical spiral data, where each spiral has different standard deviations. And if we start to play with different length scales, we arrive in some point where if the length scale is small enough, you are separating the spirals, but you are segmented the spirals into little chunks. Even the spirals are not mixed, you are not obtaining the optimal solution. And if you increase the length scale, in some point you are mixing the spirals, where the length scale is so big that the potential is so big that really there are two big potential wells here, and you are mixing the spirals. So here, there is no an optimal solution if you play with the length scale. You need to add another hyperparameter. That hyperparameter is based on, okay, imagine that is a potential well, another potential well, potential wells around here. That potential wells in somehow are connected. If you measure the difference in energy between one potential well and another, you can find that in that topology, there is some group of potential wells that from going from one potential well to another, the energy involved is very small compared with that valley and with that valley. And if you try to cross that valleys from one side to another side. So it's just, we can define like a hierarchical merging the clustering in terms of the energy involved between going from one potential well to another potential well. So if we introduce that energy threshold into the average and negative low likelihood, we can see how, in spite of the, if we look for that direction, is the length scales, and we look that direction is the energy threshold. Exists in some data some stability region here. That means that if we increase a bit the energy threshold, we can merge some potential wells that practically the difference in energy between some potential well and another are very low compared with the other potential wells. So just scanning different length scales and different energy threshold for each length scale, we can find that here there is a stable region where point out that for that length scale and for that energy threshold, we can obtain the perfect solution. And that complements very well the whole problem. And the idea is just starting from an unsupervised model, we can define completely the best model that fits the data. So just finishing here with the conclusion, we could say that it's a novel framework for detecting the underlying structure of the data. It's the underlying structure because here we can see each local minima means that it's a different structure in the model. When we change the length scale, we are assuming that our model is different. It's different because each Gaussian is completely different and the potential is different, so the clusters are different. But also we can provide a solution, and a hierarchical solution of each length scale that complements the structure of the data. So also it's a Bayesian framework. We can deal with outliers. We can play with the energy threshold, and we can assess which is the correct number of the clusters because the number of the clusters are related with the length scale. We can go back to the, we can see here that graph. Oh. Okay, here. That are the number of clusters. Obviously, with the smallest length scale, the Gaussians are very narrow and appear a lot of subclusters. But if we increase the length scale, the wave functions are smoother, are biased, and at some point you find the trivial solution that is a big potential well when you find one single cluster. So that is the trivial solution. We try to avoid that kind of solutions. But there is some dependency of the length scale and the number of clusters in quantum clustering. Oh, sorry. So there is some drawbacks, but that are related with, in general, with the quantum clustering, because the quantum clustering is based on relative distance. I'm finishing. So are based on relative distance and are Euclidean distances. So when you are dealing with high-dimensional data, because in high-dimensional space, the relative distance between one point and another point, more or less, all distances are similar, there is some problems when you try to find out which is the wave function or the potentials based on the length scales, because in some point, or you are discriminated all the points or none of the points. So the quantum clustering has problems with dealing in high-dimensional spaces. But that can be addressed if you combine the quantum clustering with a non-linear dimensionality reduction, like manifold learning, for instance, TSNE, isomap, or minimap algorithms that reduce the dimensionality, and then you can apply the quantum clustering in that subspace. Other pending point is the runtime optimization. That is future work, because most of the functions of the quantum clustering are computed on all observations and then summed together. We can parallelize that kind of operations, let's say with GPUs, multiple CPUs, or distributed computing like Spark or MapReduce, because we can map all the functions into all observations and then sum together to find the final potential and the gradients and the wave function. So that's all. Oh, that's the main references. That's David Horn and that Vincent with the manifold parsing window. That's all. Thank you.
Thank you very much, Raul. Yes, Nathan.
Thanks.
Yeah.
So one of the challenges always when you're using, as you alluded to, k-means or clustering is the value of k that you end up choosing. We had a lot of great success determining the value of k using Bayes factor analysis. Have you taken a look at Bayes factor analysis or any other methods for automatically figuring out what the right k is?
I mean, if you compare with k-means, that is completely, and is the complementary algorithm, because k-means has suffered a lot with non-spherical data because tends to segment the data into spherical clusters. Of course, there is some tools with k-means and other cluster algorithms to define which is the optimal k, but here quantum clustering is powerful is because there is no dependencies of the shape of the clusters. You can find some funny shapes of the cluster like spiral data or high density with sparse density clusters. So there exist other algorithms, but quantum clustering in that case outperforms because it's unsupervised and gives you a probabilistic framework that can deal with funny shapes of the clusters. And I mean, that's the advantages of the quantum clustering. Of course, there is other similars to that is dbScan or a mixture of Gaussians. But mixture of Gaussians, you have to preset the number of Gaussians. And here it's automatically detected with the scanning of the length scale. Of course, you can just assign some length scale, but you need to iterate the quantum solutions from, let's say, 10, 20, depending on the grainet you want. But you need to perform several times the quantum clustering just to find out which is the optimal solution without knowing the true answer. So much more or less that the advantages comparing with other algorithms.
Okay, so maybe one quick question more for Raul. No? Okay, so let's thank Raul again.